Hello, I'm Bhavani from the University of Texas at Dallas. This is a recorded presentation of the keynote address I will be giving at IEEE Smartcloud on October 8th, 2022. And the presentation will be held in the morning of October 8th, Beijing, China time. And so I'm recording this presentation. It's just after 1:30 a.m. Dallas, Texas, USA time, that is Central Daylight Time. And so I'd like to thank the conference organizers for inviting me to give this keynote presentation and hope to see you virtually. The conference will be a virtual conference. Hope to see you virtually on October 8th. And so I'm going to share my screen. Okay, so my presentation is going to be on trustworthy machine learning, that's TML, with applications in IoT, Internet of Things systems. And in particular, the application is going to be Internet of Transportation system. And so it's going to be in three parts. Part one, trustworthy machine learning. So I will discuss an architecture, and then provide some discussions on big data security and privacy, privacy-aware quantified self, data science, machine learning, AI for cybersecurity applications, how do you secure data science, ML techniques, and then trustworthy analytics. So a number of topics that comes under trustworthy machine learning. And then part two, I will talk about security and privacy for Internet of Things, in particular, Internet of Transportation systems. And part three essentially applies part one to part two. And I'd like to thank all of our sponsors, acknowledge them, and also my colleagues, Professors Alvaro Cardenas, Murat Cantagilu, Latifa Khan, and our former PhD student, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so part one is integrating cybersecurity, AI, ML, data science. So first is, what is trustworthy machine learning? Because we are applying machine learning for almost every application. And these machine learning techniques have to be trustworthy. And by that, we mean they have to be secure. So we have to handle cyber attacks, right? So machine learning techniques could be attacked. And so handling cyber attacks to machine learning. Privacy preserving, that means we ensure that one cannot deduce private information due to machine learning, because with machine learning, you can, and data science and so on, you can dig in and make all kinds of inferences, and as a result, privacy of individuals could be violated. They have to be accurate, right? Have high integrity and produce correct results. They have to be dependable, handle faults and recover from failures. And they have to be fair and unbiased, not discriminate against individuals. So I wrote a paper recently, IEEE Intelligent Systems Journal. And so this is the architecture. So it's sort of a 4-layer architecture. So infrastructure, but trustworthy machine learning is cloud-based on Hadoop MapReduce, or it could be Spark, any type of cloud-based system. And then on top of that, we host big data management, because you need lots of data to learn, and also for testing and training and so on, lots of data. So you can use systems like HBase and Hive to manage the data. And then the machine learning layer. So this is sort of the data science, machine learning, the analytics layer. So deep learning, decision trees, support vector machines. And then the application layer are the applications like IoT, Internet of Things, social media, cybersecurity, and so on. Because machine learning is being applied for almost everything. And the application could be healthcare, finance. And then the left-hand side, you've got to ensure these machine learning techniques are throughout the entire 4-layer architecture. It has to be secure, ensure privacy, has to have high integrity, availability. On the other side, fairness, unbiased, anti-discrimination. So they have to be fair. They should not discriminate, such as giving loans based on a person's gender or ethnic origin and so on, right? So this is the architecture. So what I'm going to focus on, not all of aspects of trustworthiness, I will just focus on securing machine learning techniques. And so that's the main, and the privacy aspects. So the motivation data mining, security, and privacy. So I introduced the idea of the privacy violations that could occur due to data mining. It was a keynote address I gave at the IEEE 1996 Data and Application Security Conference, and later another keynote at PAKDD, Pacific Asia Knowledge Discovery, in 1998, and subsequently published. I call it a landmark paper because I was a program director at NSF, and that was in 2002, and I wrote a paper. So when you're a program director, you give out funding money, and so everyone sort of refers to your paper, right? So it had a lot of citations. It spawned a new area of research. At the same time, researchers at IBM Almaden, they were developing this whole idea called privacy preserving data mining and the techniques. So the whole idea is that you have the original data, you perturb, randomize, so add some noise. So you've got the modified data, and then you have a modified data mining process, and the final result has to be the same. Essentially, the distribution shouldn't be changing. And so because what's the point in modifying if you're going to get incorrect results, right? So our research, then I joined academia in 2004, and we had a PhD student, Dr. Li Liu. She focused on privacy preserving decision trees, and in particular, the perturbation method. And then now with big data, data mining, security, privacy is exacerbated with big data, data science. And so I hosted a NSF workshop on big data security and privacy in September 2014. And presented the results to the interagency working group in February 2015. So at that workshop, these were some of the findings. So we said, due to the technological advances and novel applications, it's possible to capture, process, analyze large amounts of data for a number of tasks. These could be for security tasks, for financial tasks, and for healthcare, and so on. So such tasks, in particular for security, it could be anomaly detection, it could be malware analysis, also user authentication. So for example, when you have to authenticate, right, you've got to collect lots of information about the user, such as not only the password, also maybe biometric numbers or biometric data for the user, iris scan and finger scan, and so on, and access control, anomaly detection, user monitoring, protection from insider threats. So when we are monitoring users, right, the privacy could be violated. So we can analyze and integrate data collected on the web. One can identify connections and relationships. So some very useful things you can do, right? It can help with homeland protection, disease outbreaks. However, the collected data, even if anonymized by removing identifiers, when you link them with other data, it may lead to re-identifying the individuals. So security tasks such as authentication and access control may require detailed information about users, like multi-factor authentication. So this information, if you are misusing it or if it's stolen, it can lead to privacy breaches. So big data management and analytics techniques, which is the machine learning techniques, could be attacked. So directions include, we've got to securing the data like access control models, privacy enhanced techniques, big data for cybersecurity, and securing machine learning. So I'm going to address each of these topics except access control. There are different types of access controls because the data is massive. So essentially what we said is that one model may not be enough. You need different types of models. But I'm going to talk about the other 4 areas. So privacy aware quantified self. We have, we are all carrying mobile devices, smartphones. It's become prevalent computing platform, billions of users. So there's a recent emergence of quantified self movement, right? So the sociologists and psychologists have come up with this quantified self movement. So personal data collected by wearable devices, smartphone apps, and so on. And it can really help us because all of this data, when you collect, it can enhance the person's life habits, right? These data are also being shared with other service providers using cloud-based services, bringing potential benefits to users. So for instance, right, wouldn't it be great if I open the refrigerator? I love vanilla ice cream and milk chocolate, so I don't keep any in the refrigerator, but suppose I have. Wouldn't it be great if the system tells me, or I get a message on my smartphone, or especially refrigerator starts talking to me and tells me, oh, you shouldn't be eating chocolates, right? So that'll be really good for me. But such data collected and shared often been carried out without the user's knowledge, right? So that could be a big problem because privacy could be violated. So data collected, say device monitoring blood glucose levels, that could be used by the insurance company to deny coverage, not only to me, but my children and grandchildren, right? So such privacy violations could easily get out of control, even if the data collectors could aggregate financial and health related data with tweets, Facebook activity, and so on, right? So to address, and there could be lawsuits and so on. To address these challenges, we urgently need tools and techniques for privacy protection of quantified applications. So our project has developed a privacy-aware, policy-based quantified self. So here is our smartphone. So it has some data, but it doesn't have enough storage, right? So it's a sort of an Internet of Things is one of those gadgets, right? So it doesn't have a lot of storage. So we may need to use the cloud for storage, and using services, we can get the cloud data, anonymized data. Some data could be encrypted. But mainly we are collecting health information, fitness, location, social media, image, video, and other sources. And what is our privacy aware quantified self manager? What is the main purpose? Of course, data collection, storage, analytics, and sharing. But the main purpose is that it has to be policy based. So policies have to govern data collection, data storage, data analytics, data sharing. And so we are essentially saying the same thing here, right? So this is our mobile device, encrypted storage. Again, we are more or less saying the same thing, lots of data being collected and some data frequently accessed. So based on access control policies, local apps, applications running on devices will be given some access to the collected data. When needed, these applications can access encrypted data on the cloud. Some cases, like we may not be, so we don't want to collect too much data. So if you're a 20-year-old person, we may not need to collect data every day or weigh the person every day, right? Because even if the person is eating a lot and puts on 5 pounds, when you are 20, it doesn't really make, a healthy 20-year-old, it doesn't make much of a difference in the sense your blood pressure is not going to shoot up from 120/70 to 160/100, right? It's not going to happen. But when you're an older person, you may have to weigh, because if you put on a lot of weight, your blood pressure can really go up. So you got to be careful, selective about what data you collect. In other cases, data may have to be deleted, and that's a big question. When we delete the data, what does it mean? Is the data really deleted? It's not like you go to a bank and store your jewelry and then you remove the jewelry and the jewelry is gone. But here, data deleted means the service provider might still keep some of the data, right? So there has to be policies to make sure to check. There are checks and balances to make sure the data is deleted. We envision that data sharing and analytics will be carried out using services. So again, here we are saying some of the data could be encrypted, some data may not be encrypted, right? And so that's the main message here is that policies have to drive data collection, storage, analysis. So for trustworthy machine learning, one aspect is the privacy. So we can do privacy-aware machine learning. And more important, because I'm using the word data mining, machine learning, data science, more or less interchangeably. So privacy, but again, to ensure privacy, we need to have policies. Policies have to guide what we have to do with respect to privacy. Okay, now, the other topic I said was data science, machine learning for cybersecurity applications. So this has been going on for about 25 years, right? You have machine learning, you have malware analysis or whatever, insider threat or whatever. You apply this machine learning tech, develop a model, training the model and then testing. But back in the old days, about 25 years ago, we didn't have the technology to develop real-time data mining or real-time machine learning. Why? Because we need real-time, right? See, yesterday it could have been by Microsoft stock. Today it could be by what else? By Apple. Tomorrow it could be by Google. The next day Facebook. The next day Amazon. So things are changing, right? Similarly, the malware is changing patterns, right? Today, it's going to be a red malware. Tomorrow, maybe a blue malware, just like COVID virus, right? Changing patterns, mutating. Malware could mutate. So we need to be able to catch this mutated malware. So we can use past data to build classification models, predict the label future instances, and helps decision making. So this is, again, nothing new, right? Build a model, train, test. But what we have is massive data now, big data streams, continuous flow of data, very common in our digital world, massive amounts of data. So what do? So like, for example, network traffic data or financial data, right? Through a firewall comes in, we build our classification model, then we test and train if it's benign, we store it in a server, attack, we block and quarantine. But the challenge is patterns are changing. One model is not sufficient, right? Every day the model might be changing. So we don't want to keep model like last year's model. So we want to constantly update the models. So we build an ensemble of models, a collection of models, and time to time the model is updated. So there could be a human in the loop, or the models can talk to each other. There's algorithms we have developed where they communicate with each other and they get updated. Okay, so we apply this to insider threat. What's insider threat? Insider threat is like bad people pretending to be good people in an organization, right? Because you hear about espionage and so on. So similarly, in a computer, you can have bad processes pretending to be some benign process like a database process or a compiler process and so on. So insider threat it's very difficult to catch this insider threat. So we have designed and developed ensemble-based stream mining, and I will show you in the next picture. Evolving collection of multiple models, right? They're dynamically updated. Result is a classifier, exhibits increased classification accuracy. We use traditional SVM, one class SVM, so supervised approach, but we also design and develop unsupervised ensemble-based. So we had number of models, number of approaches, graph-based anomaly detection called GBAD, okay? And also, we also developed compression-based models, like look at all the words and we compress these words. And so because unsupervised, we don't have the labels. So we tested both unsupervised and supervised, and unsupervised actually performed better, gave us better accuracy, but we combined both algorithms. So, right, so that's the main key idea. And so we applied it to evolving the insider threat detection. So a person is typing away, system calls, and you have I chunks, right? And then you train, and so you extract the features and then build an ensemble of models, either using supervised, unsupervised, a combination of both. And then that's for the I chunks, as the ith chunk arrives. And then once you train, then the I+1th chunk arrives, extract features, and then you test. So the main thing, the challenge here, the new stuff here, is the ensemble, collection of models and the model updates, right? Our paper talks about the various aspects of updating the models. Okay, so the second, the other topic is securing data science, right? That means the machine learning techniques could be attacked. So what do we mean by that? Adversary modifies data to defeat the learning algorithms and understanding adversarial learning. It's not concept drift, it's not online learning. Adversary adapts to avoid being detected. During training time, data poisoning, testing time, you can modify the features. So it's a game that's being played between us and the adversary. So the adversary is trying to figure out what is the data that we are using and what's the model that we are developing, and tries to thwart us, the data and the model, okay? So what happens here is that you have, okay, all these red squares are the bad instances and the blue circles are good instances. This is a support vector machine boundary. So the adversary is watching us, right? It knows here is a boundary. It's trying to push, see what happens. There's many bad instances below this boundary so that they won't be caught. See what happens. 1, 2, 3, 4, 5 bad instances not caught. So that's what we have to prevent. So we've got to understand what the adversary is up to, and we've got to modify our support vector machine algorithm. And so before we talk about the algorithm, what's the type of model, the attack model? So attack model, we have two types of attack models, free range and targeted. Free range, adversary can modify malicious data anywhere in the domain, right? So we can put this, we can place the malicious data in this within this targeted range, right? Within this range. And then another model is a targeted attack. The paper describes, in the KDD actually, it appeared, describes our model. And so what do we do actually? So this is the support vector machine boundary, right? The dashed lines, the black dashed line is a support vector machine classification boundary. The green circles are good instances. The red crosses are bad instances. So we learn about the adversary and we try to move this, this line to this blue line, right? So we try to see, it's not magic. We have to do lots of mathematical computations and then move this line to this line here, right? By doing that, see, some of these bad instances, which we thought would have been good, because adversary is trying to push these red crosses, right? Bad instances, they are now labeled as bad instances, right? They are not being labeled as good instances. And this is actually better because the black here looks at how the bad instances are being pushed, and a lot of the bad instances are being caught. Now you can ask the question, why don't we move this blue line right here? Then all the bad instances will be caught. But if we move it here, then the green circles will be labeled as bad instances. So we are going to get many false positives. We want high accuracy. We don't want false positives. We don't want false negatives, right? So that's the whole idea. So threat model, test time, deployment time attacks, attacker modifies X to X prime, modify packet length by adding dummy bytes, add good word to spam email, add noise to an image. Black dashed line is a standard support vector machine boundary, and blue line is the adversarial support vector machine classification boundary. Okay, so that's a blue line. So that's adversarial machine learning. So this finishes, okay, so another area is trustworthy machine learning, right? So machine learning techniques have to be secure, private, and so on. Computations over big data requires massive computational resources. So often we send it to third parties. And when we send it to third parties to carry out all these computations and do machine learning, data becomes corrupted, inherently becomes available in untrusted environments. But as a result, there could be man-in-the-middle attack, a lot of attacks to the data, right? So we are conducting research in using Intel's SGX platform, right? Trustworthy analytics using advancements in embedded hardware technology, Intel SGX, to support trusted execution environments. Also, formal methods for machine learning include logics for specification for deep learning and the verification of the machine learning algorithms. So in the UK, they are quite advanced here, because I was on a panel with a professor about a year and a half ago. She was at University of Oxford, and she was applying some sophisticated formal methods for machine learning. Okay, so here's the Intel's SGX platform, and I'm not going to go into the details of the Intel platform, except to show that there is the SGX enclave memory, and we can execute some of the machine learning algorithms. These are sort of, you can think of them as trusted locations. So it's hard to attack. These are trusted regions. And so you execute your critical code, critical software in the trusted regions. And so that provides some guarantee for security. Okay. Now we go into Internet of Things, Internet of Transportation. Internet of Things, so Internet of Home Things, right? We have Internet of Medical Things, Financial Things, and so on. Internet of Home Things, you've got your cell phones, or smartphones talking to your refrigerators, talking to your clocks and your television and your Amazon cart, and everything is talking to each other, okay? So all these tiny gadgets. Similarly, Internet of Transportation, you've got the cars talking to the trucks and talking to the trains and so on, right? The roadworks, everything talking to each other. So Internet of Things, major implications for transportation. Autonomous vehicles aim at improving day-to-day activities, such as delivering packages, improving traffic, and so on. In the US, trucks alone carry estimated 63% of the freight of goods. Autonomous vehicles, not just limited to ground vehicles, They also include aerial vehicles, such as airplanes and drones, and sea vehicles, such as boats and ships and submarines. Levels of automation for AVs range from 0 to 5, with current ground vehicles in the market having partial automation at level 2, and aerial vehicles having high level of automation at level 4. Companies have invested heavily. GM spent about 728 million in 2018, and I read 1 billion in 2019. I need to get the 2020 and 2021 figures. While there's great potential in AVs and the improvement it can also do, to the transportation industry, very good things, but security and privacy concerns pose major challenges. Okay, so security autonomous vehicles. AVs evaluate the environment using a variety of sensors like cameras, GPS, inertial measurements, LiDAR, radar, and so on. Previous research has shown sensors are susceptible to malicious tampering, IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing. Vehicles should verify the veracity of sensor signals before acting, right? So, because these are tiny devices, right? So you don't have all the time and space and storage. So they're sensor-based. So AVs rely on sensors to evaluate and interact with their environment. Inherited issues, sensors are susceptible, as we said, to GPS, spoofing, transduction attacks, and manipulate environment, physical signals, visual, sound, magnetic. And classical computing security, such as memory protection, cryptography, and authentication, does not protect against these types of attacks. Due to the real-time constraints, AVs trust and act upon sensor data without any form of verification. Okay, so again, the real-time constraints, that's a challenge. So what did we do? We designed and developed a physics-based anomaly detector. That means we have to model the AV, take the physical properties and model the AV. And we built a reference monitor using physics-based anomaly detection, PBAD, for ground and aerial vehicles. The algorithm has many parts. We build a model offline, use all the physical properties. So we need control systems engineers to look at AVs. And so my colleague, Professor Cardenas, is a control systems engineer and a cybersecurity specialist, implementing an online tool to monitor expected and observed behavior to detect anomalies and raise an alarm if significant residual difference exists between executions, offline pre-processing, online verification, and anomaly detection. And the detailed design, we take for the offline processing, building the model, right? Look at the state, input measurements, and pre-processing and predicted states, XYZ, moments of inertia, mass of vehicles, drag factor, and so on. The AVs invariants are calculated, and you can see all the parameters here using a well-known nonlinear models for aerial and ground vehicles. Accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis is used for the aerial vehicle. Vehicle positioning and steering angle is used for the ground vehicle. Online stage, we used extended Kalman filter. We didn't use sophisticated machine learning. Kalman filters have been around, and control systems engineers have been using it for decades. Is used to predict AV's physical behavior by estimating unknown parameters from noisy sensor inputs. The algorithm is divided into two sections, predicts and corrects estimation before it is compared against the sensor data. So when it's compared, what we do, the anomaly detection, a CUSUM, KUSUM algorithm, is a statistical algorithm, is then used to detect persistent attacks. And then you raise an alarm if the residual difference is larger than a predefined threshold. So it's again, we are using extended Kalman filters, but the challenge is coming up with a model. That's the main thing here. Okay, so a physical implementation, we did it with drones and cars, not submarines or sea vehicles. So air vehicles, aerial vehicles, and the ground vehicles. So aerial vehicles, we had Intel ready-to-fly control drone. Controller is PX4 flight controller, focused on detecting GPS spoofing and gyroscope attacks. So we detect the GPS attacks after 0.2 seconds, while gyroscope detected after 1.5 seconds. Overhead was about 5.4332%. The ground AV, custom built on top of Traxxas Ford Fiesta. Controller is ROS Kineticam, focused on detecting visual attacks on the camera. Attacks detected after 0.1 seconds. Overhead introduced is 2.25%. Each threshold produces a probability of false alarms of approximately 2%, which is still high. And the overhead here is 5.4, and ground was better, 2.25. But the threshold false alarms was 2%. I mean, 2% would have been fine maybe 20 years ago, but now we need to get to 0.000%, okay? And then, of course, privacy. Without a doubt, machine learning is being applied for a number of applications for autonomous vehicles and so on, right? Beyond the security of individual vehicles, transportation sector could greatly benefit supporting infrastructure, allowing communication between vehicles, motion sensors, lampposts, and surveillance cameras, and give us the best routes to go and best advice and so on. But from a user's perspective, privacy concerns arise from all the information needed by such systems. So a lot of information is gathered, our driving patterns and where we are, our location, everything is out there. And we may not want that. And legislators, engineers, and scientists should keep privacy concerns in mind, because if I know that privacy is going to be violated, I may not have all these gadgets in my car, right? I may go back to like a 1960s or 1970s, 80s car or 1990s, right? So so again, if I know that I'm going to have some level of privacy, because I don't want them to look at my driving patterns, or I'm smoking in the car and sending all the information to to my insurance companies. So privacy is important. Okay, so part 3 is applying part 1 to part 2. Of course, we looked at extended Kalman filter for detecting anomalies, malware. But data science, AI, machine learning, how do we apply? Internet of transportations are subject to attack. Streaming, lots of data being collected, right? Streaming data, right? Including autonomous and in the future, driverless vehicles. So when we applied extended Kalman filter, we didn't look at sort of streaming data, but we don't have a sort of a small amount of data. It's massive amounts of data generated by millions of tiny devices. That's the challenge we are faced with. So as transportation systems go electric, we need energy conservation, threats due to such systems. I mean, we might get stranded in highways and loss of lives. So machine learning techniques being applied to analyze the data, can stream analytics being applied to say financial data and so what we applied for financial and telecom, can we apply to transportation data? That's a question. And we are conducting research in that area. And the main question is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on massive amounts of heterogeneous sensor data. So that's the biggest challenge that we have. Of course, adversarial learning is another problem, right? Because we are applying machine learning for transportation systems, Internet of Transportation. It's going to rely heavily on data science machine learning for various applications, optimum directions, driving without a human in the loop, and so on. Adversary is there. It's going to watch what we are doing, our models, learn our data, and it's trying to thwart us. It will attempt to thwart the vehicle's learning process. It can cause us, we can get into so many accidents, right? With all this malware, it's learning. So therefore, the learning algorithms have to adapt because adversary is going to thwart us and cause really problems and havoc. So we have to be several steps ahead. Eventually, it becomes game playing between the adversary and the vehicle's machine learning algorithms. What sort of game? Zero-sum, Bayesian, need to understand the data. Research on this topic is only beginning. So privacy-aware policy-based data management framework for Internet of Transportation. So again, remember the picture I showed with our smartphone, but instead now we have a car. Radar, GPS, cameras, LIDAR, ultrasonic, instead of social media, healthcare, and so on, all the data is coming from here. Some data could be encrypted and stored in the cloud. With cloud-based services, we can retrieve the data. We will have this gadget inside the car, and then we'll have data collection, data storage, data analytics, and data sharing, but it has to be policy-based. Policies have to govern what sort of data we collect, how do we store and access, how do we analyze, how do we share, right? Policies have to govern. We haven't started this research yet, but we are looking into it. And hopefully we can get some funding to do this type of work for this particular area. Okay, my last chart. Developments in integrating cybersecurity and AI are exploding. Applications of AI for security inside a threat and security for AI, adversarial machine learning. Also developments in privacy-aware healthcare and managing one's life's activities. So I talked about privacy-aware quantified self. At the same time, with IoT and Internet of Transportation, security and privacy solutions being developed. For transportation, mainly physics-based solutions. As driverless cars become a reality, more and more AVs will use machine learning. How can we develop AI solutions for detecting malware in AV systems? And how can adversarial machine learning work for autonomous vehicles? Can we develop a privacy-aware policy-based framework, data framework for Internet of Transportation? Is it possible to perform trustworthy machine learning? Okay, analytics efficiently when so much of the data is coming from all directions, like formal verification of machine learning. How can we provide some of the other features which I haven't talked about, right? Because I mentioned about trustworthy machine learning, not just security and privacy, also integrity, dependability, and fairness, and numerous opportunities for substantial research and development. Okay. And I'd like to thank my colleagues again, Professors Alvaro Cardenas, Murar Kantajulu, Latifah Khan, and my former student, Dr. Ralph Quinones, and our project coordinator, Ms. Rhonda Walls. And so, yes, so I'm going to stop sharing. And again, I have, right, I mean, I tried to sort of rush this presentation because it's a little bit late, and also it's a recorded presentation. And usually this takes about 45 minutes. So I tried to finish it in, I don't know, about 36, 37 minutes. But again, on October 8th, I will be there, and I will be happy to answer questions and also explain some of the concepts in more detail. And so the main thing right now is to send this presentation to the organizing committee, because my deadline is almost there. I've got a few more hours to meet the deadline. And again, thank you so much for listening to the presentation. And I will see you, I'll be live, sorry, not live, virtually live on October 8th morning, Beijing time, China time. Thank you very much. And I'm going to now stop the recording.